right, we really want to focus on explaining and using the principle of superposition of waves to account for interference. So remember, interference is this repeating pattern of maxima and minima, places of reinforcement and cancellation due to constructive and destructive interference between two coherent waves. We want to explain experiments that show diffraction and interference and solve problems involving two-slit and multiple-slit interference. So I'm going to kind of focus on the mathematics of solving problems for two-slit versus multiple-slit interference and how you can sort of recognize when it's a two-slit type problem or a multiple-slit type problem. Diffraction is the spreading out of a wave as it goes through a narrow opening, like you're seeing here. So the spreading out of this wave. So this little experiment here, sending a wave through a narrow opening, sort of shows that. A diffraction grating is a bunch of little lines that the waves are going to spread out. So you're going to have a lot of sort of chances to interfere. And so multiple slit interference, you're looking for a keyword like the diffraction grating. There's a diffraction grating. Okay, so that's a lot of slits. Two-slit is like you see here. And if it's a multiple slit diffraction grating question, then the first thing that should come to mind is the equation d sine theta equals n lambda. Let me write that again a bit more clearly. If it's a diffraction grating, multiple slit interference type problem, d sine theta equals n lambda, where d is going to be the distance between the slits. So there's going to be lots of slits and there's going to be a distance between them. Theta is the angle that the light diffracts out to. So you're going to see that there's going to be, again, this alternating pattern of maxima and minima, and there's going to be a zero order maxima. That's the exact sort of midpoint over there. So there's a zero order maxima. There's going to be a first order and a second order, maybe a third order. But the waves can't diffract more than 90 degrees, right? So we're sort of limited, to 90 degrees. It's the angle just from the zero order down to whichever order, n is the order number, okay? Lambda is the wavelength of the light that's being diffracted. So if there's, orders 1, 2, 3 sort of below the zero order, the diffraction grating will also diffract, the wave up this way. So it'll be sort of orders 1, 2, 3 above. But the angle theta is just the angle to, any given order, right, from sort of the zero. So keep that in mind because we'll see problems that will have us use this equation to solve for how many sort of bright spots will we see. We have to solve for the number of order that would be visible. That's where we're always going to maximize theta at 90 degrees and just calculate what is n. But n will only tell us the number on one side of it, right? It's like for this example, if we calculated n for a given wavelength of light that got diffracted and all these, slits in the diffraction grating, and we saw that there was 3 bright spots on this side, there was a bright spot here at the zero order, and 3 bright spots over here. Keep in mind that when we calculated this, we would solve n equals 3, right? Because we're only solving for what is the angle to sort of any given order. So if we sort of plug in 90 for this, we knew the distance between each slit D, we plugged that in, we plugged in 90 for this to maximize this term, right? We can have a sine greater than 90 degrees. And then we plugged in the wavelength that was given, we'd solve for n, and we get, some number that would, either be 3 point something, and we say we can't have a point of an order, so we'd have to round it to sort of 3 there. If it was 2 point anything, you have to round it down to 2. If you don't have the third order, it's not going to be a bright spot. You always have to sort of round down to the nearest whole number. But then the answer to the question, how many bright spots would you see if you sort of had a screen that collected them all, sort of like a screen over here, you would actually see 7, right? You'd see 3 on this side, 3 on this side, plus the zero order. That's a very typical question. And you'll see different variations of it where you have to solve for the number of maxima or the number of bright spots or the number of loud spots if it's a sound wave. And keep in mind that this equation gets you part of the way to the answer. You have to remember to double n to get the other side and then add in the zero order. So the path to the solution for that type of problem, where it asks you to identify the number of maxima for diffraction grating, a multiple slit interference problem, is to substitute in 90 degrees for theta, because that's the maximum sort of value for sine theta. The light can't diffract more than 90 degrees, right? Backwards. So plug in 90 for that, plug in the information that was given in the problem for d and for lambda, and solve for n. Once you know n, double it, double n, and then add 1. So that's sort of the last step to solving a problem, like identify the number of maxima if you know that it's a diffraction grating problem. Sometimes the information isn't given to you as friendly as here's the distance between the slits, but they'll tell you n, the number of lines per meter. They'll say, here's a diffraction grating with, 4,000 lines per centimeter or per millimeter, something like that. And then you have to calculate, well, what's the distance between each one then? It's going to be 1 over n, right? And make sure you convert it. Usually you want it in meters. Same thing where your wavelength is going to be in meters, distance in meters, right? Everything's sort of there. So n is just a number. So this is the other sort of little wrinkle to those problems. Sometimes the data isn't reported as friendly as here's the distance between the slits. It's here's the diffraction grating with 4,000 lines per centimeter or 5,000 lines per millimeter. And then you're saying, okay, in 1 millimeter, if I've got 5,000 lines, then 1 divided by 5,000, we'll solve it. But always convert to meters like we saw with the very first warm-up question, paper 1. You got to know your metric prefixes. If it's that many lines per millimeter, centimeter, right, convert into meters. So this is the key equation for diffraction grating multiple slit interference. When you recognize it's 2-slit interference, though, we're going to use a different equation to sort of make sense of that. But mathematically, it's sort of much the same as this. You just sort of get sharper interference patterns when you use diffraction grating because a lot of waves are going to sort of construct and make the bright spots, and a lot of waves sort of cancel out. So you get sharper sort of fringes when you use diffraction gratings versus just a 2-slit. Here's a 2-slit, right? What's the clue that we're going to use the 2-slit sort of equation? Double slit, right, might be a good indication that that's a 2-slit type of problem. Here's the key equation you want to keep in mind when it's 2-slit. Remember, diffraction grating, we just talked about the d sine theta equals n lambda. Now it's 2-slit, and we want lambda equals ax over d. Okay, that's something to put down in your notes related to the learning objective solving problems using 2-slit interference. This laser has a given wavelength. That's the lambda. These slits have distance between them, right? It's 2 slits, but there's a distance between them. And we saw in the video that the more we sort of spread those apart, that will have an effect on how far apart sort of these are over here. So the distance between the slits is called A. A is the distance between the slits. This value here is capital D, the distance between the source of the light, between the diffraction grating or the 2-slit, and the screen where we're detecting the interference, right? This alternating pattern of bright, dark, bright, dark, bright. So every sort of crest you see on this waveform, they're labeling it as a bright fringe. And the dark spots would be sort of where there's the trough of the wave is right there. So X is the distance between those two, any two bright fringes. Okay, X is the distance between them. Now they don't tell us what X is. They tell us that between 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 bright fringes is 12 millimeters. So there are 12 millimeters per 9 bright fringes. I just kind of write it out like that. 12 millimeters per 9 bright fringes, right? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, oh, per 10. If you go from this one to this one, it's like how many distances are there? There's 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? There's 9 distances between that 12 millimeters. It's actually 10 bright fringes. But if you look at like we're calculating the distance between like any two of these, to say, well, how many of those distances to get from this one? It's like get from that one to this one. There's 1, 2. So it's actually 9 of those distances in these 12 millimeters. So 12 millimeters per 9 lengths means each length is 1.3 repeating millimeters. And so that's what X is. It gives me enough information to calculate X. They've given me B. I don't know what A is, and I don't know the wavelength, but they tell me the laser emits light of frequency 670 terahertz. So we can anticipate the calculations that we have to do here. We're going to have to figure out what is the distance between these slits, right? Because A is really the only unknown. They don't give us the wavelength, they don't give us X, but they give us a way to calculate it. And we already calculated X, from the information that they gave. How can we turn this frequency into a wavelength, plug into the equation? You may recall earlier today, we explored this idea. And now it's coming back to help us. We know the speed of light's always the same. This is a laser, right? Light, the L in laser is light. So there's the speed of light, and we'll divide it by this frequency, 670. Something else we did today coming back to help us, right? We went over all the metric prefixes that are relevant here in this course, and we said that tera is like not a gigabyte drive, 10 to the 9 bytes, but we got a terabyte drive, a trillion, tera trillion. So 10 to the 12. So if we divide 3.0 by 10 to the 8, the speed of light, divided by 670 by 10 to the 12 frequency, we can get the wavelength lambda. So let's do that. 3 by 10 to the 8 divided by, open parentheses, 670 by 10 to the 12. 670 nano, 6.7 by 10 to the 14. So it's in sort of the visible light part of the spectrum. It's 447 nanometers, or your calculator here might show 4.4, let's round it to 8 by 10 to the negative 7. That's the same thing as 448 by 10 to the negative 9 meters, which is 448 nanometers. So this is closer to the violet part of the spectrum. 400 nanometers would be purple light, and so maybe a bit like a blue purple laser. Pretty cool. We have a purple laser. Oh, that would be the Mace Windu lightsaber. This wavelength. All right, so we can plug in now. Let's solve for A. So the clean way to do that is to make A the subject, and that means we multiply both sides of this by B over X. Right, and we cancel out those and those. So A is equal to D lambda over X, D 2.8 meters. Lambda, we just calculated 4.48 by 10 to the negative 7. And X we said was 1.3 by 10 to the negative 3. So I still have that 4.4776 and so on by 10 to the negative 7 in my calculator. I'm going to times it by 2.8 to solve my numerator, which is 1.25 by 10 to the negative 6, divided by, open parentheses, 1.3 by 10 to the negative 3. This gives me a distance A equals 9.6 by 10 to the negative 4 meters. All of these quantities were in meters. So that's how you go about sort of thinking through solving a problem with two-slit interference. Note that you might have to solve for any sort of one of those variables in that equation. So make sure that you understand the equation for two-slit. Lambda equals AX over D. Perhaps spend some time constructing a figure similar to this one and label everything clearly with, what's the wavelength, what is A, what is D, what is X. It's all really just geometry, right? We're just relating sort of distances here. As as a bonus challenge, try to sort of see why this is true by constructing some triangles and proving it. We'll leave that for another course.